discussed a bit of the general properties of root systems using Dynkin diagrams. I don't remember whether I have discussed all the root systems. So there's a chart of the various kinds of root systems that you can possibly have. Did I give it all last time? Probably not. Okay, so I'll do this on one side. So remember once again that the root systems were the primary tool in describing root systems was to represent simple roots by blobs and the angles between them by some kind of single bond, double bond, triple bond, or disconnected blobs, which means that the angle between them is, so this is the angle of 120 degree, this is the angle of 135 degree, this is 150, and this is 90. I should probably have written that over here. So these were the various angles. The lengths could possibly be different of the various simple roots. So I'll come to that. So whenever there is a non-single bond, like a double bond or a triple bond, the lengths of the two roots are going to be different. Okay, and so with that little bit of data last time, we said that if there are indeed just two blobs and connected by a single bond, we constructed the SU3 algebra out of that, right? Certainly for SU2, which is a single blob, okay, we constructed the J plus, J minus, and J3 from that, and I think I explained how that goes. All right. Okay, so you can carry on and you can construct all Lie algebras like these. This is called the AN series. This represents SUN plus 1 or SLN plus 1C. These are all complexified notations. So, you know, when one talks about SUN plus 1, one has you know, the particular real form in mind. Okay, so namely in terms of you know, this is like talking about SU2 versus SL2. So when you are talking about SL2C, it could have it encompasses SL2R as well. Okay, so these are all various kinds of Hermitian generators that you choose to. But when you are talking about Lie algebras over complex fields, this and this are the same. Okay. Then there's a B guy that goes like this. Okay, and so let me not confuse the. Let me use what we have been saying so far, and this is called DN, and this corresponds to. This corresponds to SO2N. Okay. All of these Lie algebras are over complex fields because we have been taking, you know, linear combinations, complex linear combinations of generators to work out the representations. So when we are talking about representations, and in particular when we are talking about the raising and lowering operators, we are taking complex linear combinations of Hermitian generators. So we are talking about here complex field. Yeah. Okay, so that's that, and then this this stuff where I'll explain what these things mean, and this is called the Bn, and this is SO2n plus 1.
So does the arrow have any meaning?
Yes, yes. The arrow says which one is bigger and which one is smaller.
All of them has n number of blobs.
All of them have n number of blobs, every one of them. So n denotes the rank, because the number of blobs is the same as the rank, the number of blobs is the same as the number of simple roots, and the number of simple roots we proved last time, that is the same as R, which is the rank of the Lie algebra. Okay, and this this is the other one, in which it is SPN, and these are the what are called the classical Lie algebras, which can be described in terms of symmetry operations on vector spaces, and these are what are called the exceptional Lie algebras. These are isolated objects. They don't form, they are not part of any class of, it is called E6. It's called E7. This is called E8. And then there is an F4, and there is a, this is F4, and this is G2.
These are the all possible Lie algebra.
These are all possible Lie algebras. Okay, so these are sometimes called classical Lie algebras, and these are called exceptional Lie algebras. I should tell you the ranges of these things. So here, you know, the SUN plus 1, you start from this. Here you start from n greater than or equal to 2, but I should 2, but I'll tell you what 2 special means here. And this is n greater than 1, this is n greater than or equal to 1. Okay. The reference that I sent today to the mailing list, okay, that has a very nice description of the root system of these algebras, the classical Lie algebras, and you can convince yourself that these are indeed the root systems of those things. It requires a bit of work. I will probably explain maybe a little a special example of this today. All right, so and this arrow means that you know, the this is a, let me get the convention right. Okay, so the convention is the following, that in case of Bn, this is the shorter guy, okay, this is shorter and this is longer, and all of these guys are long. Whenever two blobs are connected by a single bond, all of them have the same length, okay, but when they are connected by double or triple bonds, then one of them is longer and one of them is shorter. So this arrow means that it's long to short, okay, and same description here. So this is the long guy and everybody else is short, okay. This is the story with Cn, and similarly everywhere else is the same story. So the arrows are from long to short. Okay, so that's the convention, and I'll tell you how this long short business comes about. But before that, let me tell you some. So first of all, okay, these are clear. The SPN algebra is defined. Actually, it's all given in that reference that I sent you. It's a very nice reference actually. So let me just give you the definition of SPN, because I have not given the SPN definition at all so far. So it's the following, that these are matrices which commute with the following commute in this anti-commutes in the following sense, that these are in two n dimensional. So let me say what. Okay, so what this J is some 2n dimensional matrix which is like this. J is a 2n dimensional matrix, and X is a complex 2n dimensional matrix which is, which satisfies some kind of anti-commutation relation with respect to J in this fashion. Okay. You may recognize what this matrix is. This is called a symplectic matrix, okay. And if you take an n-dimensional, 2n-dimensional phase space, okay, then the symplectic form of the 2n-dimensional phase space, okay, written in terms of a matrix, would look exactly like this, okay. So it would be some dq I wedge dpi summation over all I going from 1 to n. Okay. So this is that. So these are like the the linear transformations. Okay, these are like the infinitesimal versions of symplectic form preserving transformations. Okay, canonical transformations. Okay, so all right, and in fact there is a particular solution for these x's also. These x's look like it's all explained in that article. It looks like ABC minus AT, where BT is equal to B, so B is symmetric, and CT equal to. So I'm not deriving any of these things. So this is the definition of the SPN matrix. So
if n is greater equals 1, in that case we will have only one blob, and if n equals 1.
So let me explain. Indeed, that is true. So for n equal to 1, okay, it's just one blob. And so here also you can have one blob AN, which is SU3. Okay, sorry. SU2. So SU2 has one blob, and this also has one blob. So just by blob counting, since we have said that a single blob would always correspond to J plus, J minus, and J3. So therefore, you already get this equality, which is true that so at small values of rank, you have this funny, you have this interesting things, that SL2 is equal to, so let me use this notation. This is the same as SLN plus 1. Okay. So SL2, which we call SU2 in terms of the particular basis that we are interested in. So SL2 is the same as SO. So there's another place where you can have a single blob, okay, which is this as well as this. So this, and this all can have single blobs, and those are indeed the same. Okay. SO3, and this we already know, that is SL2 is the same as this one, and this is SP1. Okay. So this is in fact true. One can show this, that this equality is true. Another interesting special case is the n equal to 2. Okay. You are supposed to extend this diagram from this side. Okay. So for n equal to 2, it's just two disconnected blobs. Okay, just two disconnected blobs. So therefore, I'm talking about D2 now. So D2. That is SO4, okay, and it's looks like this, two disconnected blobs. What does it mean? That means that it's two disconnected SU2 algebras, and in fact it is true. Okay, you can show that SO4 Lie algebra is two disconnected SU2 algebras, and this is the reason why when you Euclideanize the Lorentzian algebra, okay, you get the fermion that you get, the Dirac fermion that you get, okay, they are the fermions of the two chiralities, they get completely decoupled. Okay, so we are talking about Lie algebra here, but in terms of the group, it is indeed SU2 cross SU2. That's right. No, for SO4 it is genuinely true.
No, and SO4 is always SU2 cross SU2, and this and no quotient group or anything. And no.
It's not this subtlety between SO3 and SU2 is not there.
I see.
As far as I remember. This is certainly true at the level of Lie algebra.
I mean, what I was remembering is this in the group SO4 and all the SU2 cross SU2. I mean, 0, 0, 0, half 0, and do they all occur? Or I remember some.
You mean you're talking about the spinorial representative, for example? Yeah. For example, in SU, in terms of the group, in the SO3 group representation, the spinorial representation does not appear.
No, in SO4, I was talking.
But in but in SO4, I think 0, half, comma, half 0.
Some are ruled out, and from some global issues.
Is by spinners, maybe SO4. Okay, so if I take a spinner of the first one and the singlet representation of the second one, then I'll get some representation which is like a spinner overall, and that SO4 will not have. So presumably, there is an issue like that. So talking about Lie algebra, this is the story, and then there are some more, which is like these two guys, okay, are if you cut out all the other blobs, then this and this become identical, because it's some long to short and long to short. So if so there are just two blobs connected by a double bond, okay, in which one is long, the other one is short. So clearly these two will be the same. So B2 is equal to C2 just by the geometry. And what does it tell you? So this equality was that A1 is equal to the same as B1 is equal to the same as C1. D2 is the same as A1 plus A1, and B2 is equal to C2. What does it tell you? That says that SO5
So the issues of the length
is the same as SP2. What?
So the issues of the length.
It doesn't matter, because when there are only two blobs, okay, this looks like, yeah, it doesn't matter. So there is a single, there is just one double bond connecting two blobs. Okay, so that's the only information. Unless there are other blobs, okay, connecting to these things, okay, there is no way to distinguish between this and that. Okay. So if there are other guys here, then you can say that, well, it is of this kind. Okay. And if there are other guys here, then you know, everybody else would be heavy or you know, long, and the others. So here, if there are other fellows, then lots of long and one short. And if these are connected like that, then lots of short and one long. But if there are only two, then one of them then is long, the other one is short. So therefore, there is no invariant distinction. And indeed, it is true that at the level of algebra, it's like that. There is one more that goes for three blobs, which is that. So you were reading from the right again. So if you cut out all the other guys, then D3 must be the same as A3. Okay, so that's another interesting thing. So D3 is equal to A3. So if you so I'm not proving these equivalences, but if I can convince you that these are, so which I'm not going to do, but this reference that I have sent, they will convince you that these are the root spaces of this. Well, not exactly, this doesn't go all the way, you have to do some work, but Georgia's book, for example, does a very nice job of showing that these are the root systems of these things. So therefore, if you remember this, then at least this is a very nice mnemonic of knowing these equivalences. Okay, so D3 is equal to A3, and what is D3? D3 is SO6, and A3 is SU4. Okay, this is the you know, important in the physics of the hydrogen atom. Okay, because SO4 actually is the symmetry of the hydrogen atom because of this Runge lens vector. So there is an enhanced symmetry for the hydrogen atom, which you might think that it has a central potential, so therefore it has only SO3, but actually it is a special central potential, which is 1 over r, and that has an additional thing, which is you know, this Runge lens vector, and that makes it SU4. So therefore, the spectrum of the hydrogen atom is arranged actually according to SU4. Okay, you know, in my days I used to read Schiff, which has a very nice description of this SU2 plus SU2 characterization of the hydrogen atom. Okay, so that, and as I said, if you Euclideanize Lorentzian algebra, then the description of spinors, Dirac spinors, okay, becomes particularly easy because the SO4 spinors are nothing but you know, one SU2 spinor, another SU2 spinor. So if you know about SU2 spinors, okay, which is just the spin half representation, then you know, you can easily take combine the SU2 spinors to construct your SO4 spinors, and once you know sufficiently about SO4 spinors, then you can construct the SO3, 1 spinors, which is the Lorentzian spinors. Okay, good. So I mean, in fact, in terms of the complexified representation is the same thing. Okay. All right. Good. So that was one thing out of the way. So yes. No. So it's not anti-commutator. It's exactly this. Okay. I can come. I'll come back to this. There's some very nice geometry of this one. Okay, which I'm not explaining right now, but it's quite beautiful. It has to do with the symplectic geometry. But let's carry on with what we have now. Okay, so last time I said that, well, suppose I have just two blobs. Okay. Then one possibility is, of course, not to do anything at all. So this would be SU2 cross SU2, or in terms of Lie algebra, it's just disconnected SU2 plus SU2. Okay. But suppose they are, I'm talking about connected Lie algebras, then these this is one possibility, and this we have shown already that this corresponds to SU3. This we have just discussed that the double bond correspond to SO5 or sp2, and let us see how that goes. Okay, today I was planning to do the triple bond thing, but that's a little more complicated. So let us see how to construct the Lie algebra from this diagram. Okay, so remember, so let me call these things as usual the two simple roots, alpha and beta. So alpha dot beta is equal to whatever is the cosine of that thing. It is minus 1 upon square root of 2. And so remember our master formula which we had, which was that 2 alpha. So these are the pictures, right? So suppose you start from some simple root alpha, and you try to construct, if there are only two simple roots, okay, then starting from alpha you can only apply beta to it. Okay, you can't start with have an alpha and apply alpha on it, because that will definitely give you 0, because it's commutator. So you can apply beta to it by the definition of it, and you will reach here, which is alpha plus beta. You don't know whether you will get a 0 here or you will get a root here. Okay, that we'll find out. Okay, but you know that you can't apply beta to lower it, because simple roots are the lowest objects. Okay, so here I definitely know that you get a 0. So the question is there a root here, or is it also a 0? Okay, that's what we want to find out. Now the height of the tower, starting from anything by applying beta, there's a formula for that. Okay, so what is it? As a height as well as the depth of a tower. So that is the following. So you take the dot product of this and that, and you divide by the mod square of this guy. This is given by q minus p, where q is the depth and p is the height of the tower. Okay. Now q here is by definition 0, because we are at the lowest. So these are so simple roots can also be called the lowest weight vector of the adjoint representation. This is something that is good to remember. So so therefore q is 0. Okay. Very good. So now so this object, now you can apply this thing here. So this is 2 into minus square root of stuff, and if you write them in terms of the hats, you will get alpha by beta, okay, is equal to minus p, okay, where p is an integer. Okay, and so what you get is that alpha divided by beta equal to p root 2, p by root 2, p by root 2, right? And similarly, you could think of starting from beta, and we'll try to find out if there are solutions of this, you know, and similarly you can start from beta, apply alpha on it, and you will end up with beta plus alpha, which is the same thing as that, of course. Okay, so you might as well say that you know, we are applying starting from beta, and we are applying alpha on it, and to see again whether this root is there or it's I hit a 0 here. Okay, so now I get that 2 beta dot alpha divided by alpha square is equal to minus p prime. So the height of the alpha tower starting from beta, that's p prime, that has to be another integer. Okay, so this again can be written in terms of the beta hat dot alpha hat, so that's minus square root, and now it is beta over alpha, and that is also an integer. Okay, so so what I get is that, let me write it this way, p is equal to root 2 and p prime is equal to root 2 beta by alpha. So is there a solution of this system with some assignment of this of value to this ratio, and p and p prime are both integers? Okay, so first of all, you can get rid of this ratio by taking a product of these two relations. You get p prime equal to 2. So you get p prime equal to 2. So there are integer solutions of this, okay, in which you have p equal to 1 and p prime equal to 2, or vice versa, p equal to 2 and p prime. Let's say I have p equal to 1 and p prime equal to 2. So then I'll get this story equal to 1, and so that I get to be, that is to say, this tower has a height of 1, okay, and the other one is this, which is 2. So the alpha tower starting from beta has a height of 2. Is it clear? So this, remember, p equal to 1 means this height, this tower has a height of 1. This tower has a height of 2. That means I can go one more. So this is, I can apply, so this is beta going to beta plus alpha. So this here is beta plus 2 alpha. Okay. Then you can calculate these you know, heights of towers. Again, you can convince yourself. Now the data you all have. Now you have determined the relative lengths of alpha and beta.
P prime equal to 2 here, right?
P prime equal to 2. So p prime, remember, is the alpha tower starting from beta.
No. So shouldn't it be the other way around then? Because you're going 2 steps up to.
Exactly. So starting from beta, I get in the first step I get beta plus alpha. Then I can go on more. Okay, so therefore I will get beta plus 2 alpha. Right? So, and there, because the height of the tower is 2, I know that after this I will get a 0, Okay, and you can show that, you know, all of so you can't get anything here, of course, because the height of the tower here was 1. So you must get a 0 here, and wherever else you could have anything, any other possibility. Yeah, you could have another possibility. You might say that let us start from beta plus 2 alpha and apply a beta on this. Okay, I don't know what the height of this tower is, but you can check that it is actually equal to 0. The reason why it is 0 is that this has not been obtained by some beta raising operator, okay, from somebody else. So therefore, if you apply a beta raising operator here, it is already on the top of some beta tower. Okay, so it must be 0. Okay, but you can actually compute the p and p prime, pq values of these things and find out. Okay, so that's it. So how many roots have we constructed? To begin with, we had the 2 simple roots, and then we got 2 more. So what is the dimension of this algebra? So we had, of course, 2 blobs, which means that the Cartan subalgebra has 2 elements. Okay, so that's H1 and H2, and then we have alpha and beta, and then we have alpha plus beta and beta plus 2 alpha, and their minuses. Okay, so it's 10. So it's a 10-dimensional Lie algebra. So it's a 10-dimensional Lie algebra, and
about the activity, because beta and alpha, and so there are 4 of, the 4 positive roots.
there are 4 positive roots, 4 negative roots, plus 2 Cartan subalgebra elements.
I see.
Okay. So it's a 10-dimensional Lie algebra. So it's, so to be precise, sum H1, H2, and then you have alpha, beta, alpha plus beta plus 2 alpha. Okay, and their minuses, negatives. So all told, you have 10-dimensional Lie algebra, and out of these things, if you look at the root systems, and so as I said already, that the 2 double bond is either here or here. So SO 5 is something whose dimension you can compute, and is of course 10. Okay, so the dimension of SO 5 is 5 into 4 divided by 2, so that's 10. Okay. Of course, it doesn't say that the Lie algebra is actually SO 5. So again, with this nice choice of basis that are given in this. So let me just say that okay, I'll just very quickly write down what the choice of.
So
Yes.
here we have 2 possible solutions of PP prime is equal to 2, and both of them give 4 roots, and this we'll have, even if you take the other
That doesn't matter. It's just flipping the role of alpha and beta. So in the other case, if you call the other one alpha, so what you will get here is that this vector will be alpha plus 2 beta.
Yeah,
but it's the same.
Sorry, I'm asking in general, if you have many possible roots, will it always have the same number of roots?
If you have many possible,
Roots, many possible solutions to that kind of equation, will it always have the same number of roots?
Let's say PP prime is 4, then
so you will, yeah. In the other case, in case of the triple bond, what will happen is that there will be the square root of. This is what happens. Okay, so if you did the case of the triple bond like this, okay, you will get PP prime equal to 3. So again, there are only 2 solutions, 1 and 3, and 3 and 1, and they are exchangeable.
So in other words, PP prime is always a prime, is it?
PP prime. So it so turns out that there are, there are some. Okay, so there this 2 blobs is one case that you have to work out, and the case of 3 blobs. Okay, that's what you have to work out. So these are like the basic units of forming Lincoln diagrams. So in this, okay, the PP prime structure is such that so okay, there's one point here, is that so you might wonder, okay, so what about PP prime equal to 4? They don't appear. So like 2 and 2 and 1 4 and 4 1, okay, but they are not there. Okay, so the only thing that you have to so for instance, there is also this thing that if you have a double bond, okay, then you can't have branchings or more complicated stuff. Okay, so just the 2 blobs, okay, they may be connected to something else, but the PP prime calculation that you do is something that is relevant only for the 2 blob case, and then you just continue on.
So with PP prime for all pairs which are connected.
That's correct. That's correct. So here, for example, exactly. So you get PP prime equal to 1 in all the other cases. As a result, the lengths of these things onwards is the same as this guy. So for instance, in this case, if this is taken to be, for the BN algebras, this is short and this is long, and the other fellows, so this, let's say if this is 1, okay, then this length is square root of 2, and everybody else is square root of 2. And here it is, this is square root of 2, this is 1, and everybody else is 1. Okay, so that is how it goes. So these possibilities in which PP prime are can have more than these, like PP prime equal to 4, they don't appear.
It's always a prime.
It's basically because of this, the number of possibilities here being very small. All right. Okay. Good. So, so that was one example that I wanted to work out. So, yeah. So so H1. So in this article that I sent you, it's a very nice basis of. So this so let me. So in the math literature, there are these special matrices which are used, okay, in which Eij is a matrix which has 1 only in the ijth place, okay, and 0 everywhere else, okay. And so H1 you can take to be this way, okay. So I mean, this particular case I can say what that is. So it's -1 0 and 0 0 everywhere else at 0, okay. And H2 is E34 minus E43. Okay, that's what, and that will be. So let me say. So it's like and 0 and 0. And here, this guy is like 0 and 0 1 minus 1 0 and 0. These are 2 by 2 blocks. This is a 2 by 2 block, and this is a 1 by 1 block. This is just one number. Similarly, this is a 2 by 2 0 block. This is 2 by 2, of course, and this is a 1 by 1. This is for SO5. Okay. So these are the 2 Cartan subalgebra elements, and okay. So then I don't have time to actually write down. So the then there are some things which look like boost generators. Okay. Which involve the last column, okay, here. Stuff coming from like 1 5 and so on. Okay, all right. So let me not get into that. You please look it up and try to convince yourself that the algebra that you actually got, where alpha beta, alpha plus beta, and beta plus 2 alpha, they actually describe SO5. Okay. Now I will wrap up this discussion and leave the rest to the literature. Okay. Now there is we come to the important discussion of representations. Okay, so representations, and we begin with examples. SU3 will give us the I'll keep this for a while. So, so again, let me write down the master formula for starting from a weight. So, last time I was doing writing diagrams like this with a bar. Maybe this is a better idea. So, I want to ask, if I apply a raising operator alpha, so that the weight which I reach is at mu plus alpha and so on and so forth, and when I apply by raising lowering operators, then so at this stage, again the master formula was that 2 mu dot alpha divided by alpha square is equal to q minus p. Okay, that's what it is. And now I will consider only the top of the tower kind of states. Okay, these guys. So these, for obvious reasons, are called highest weights. Okay, because and they are highest weights with respect to any raising operator. Okay, so if you apply E alpha, then it will be annihilated. If you apply E beta, it will be annihilated, and so on and so forth. Okay, so then this for the highest weight vectors, P will be 0 because there is no tower above it. Okay, so these are the highest weight vectors. So raising operators will annihilate that, and therefore this statement will be true. Okay, this is a general structure of the highest weight vector. And in fact, as I said, this statement will be true for any of the simple roots. Any of the simple roots, okay, will annihilate it. Yes, that's correct. Okay. Now you can see from here that I am giving the projection of mu onto R number of linearly independent vectors. Okay, and these are given by Qi's. So clearly, if I give the Qi's, I am specifying mu. Okay, so any mu, so any highest weight, okay, can be completely specified by these positive integers Q1 to Qr. Right? So basically, it just says that what is this? So this is the depth of the tower starting from mu. The depth of the tower along alpha 1 is Q1. The depth of the tower along alpha 2 is Q2, and etc. etc. Okay. So these depths, if I give them, give you that, then I have completely specified the you can invert this. You can find out, you know, you can show a thing like this, that mu is some linear combination of ai alpha I, and you can find out these AIs in terms of these QIs. Alpha is at the simple roots. Yeah, yeah. That's all I need. That's all I need. Okay.
R is the dimension of the weight space.
Sorry?
R is the dimension of the weight space.
No. R is the rank. R is the rank. R is the rank. Okay. So this vector notation, whatever vector notations I am giving here, they are always R dimensional vectors. Okay. That is the thing that is kept implicit. Okay, so that's the thing. Now there's a special set of highest weight vectors. Special set of highest weight representations. In fact, these are called fundamental representations. Fundamental representations.
Is that a technical term?
No, well, it's just fundamental representation. So I'll tell you what the special thing is that one of the integers is 1 and everybody else is 0. Okay, so these 1 0 0 0 0 1 0 la 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 0 0 0 1. These guys are called fundamental representation. They are all highest weight vectors. So this. Oh, by the way, I should say that, well, in fact, this is an order pair. I should not write. This is a set notation. This specifying these integers, okay, is of course equivalent to specifying the highest weight representation. And as we have indicated for SU2, and also I have briefly mentioned for SU3, that once I give the highest weight vector, I can keep applying all the lowest weight vectors, and the representation that you get will be an irreducible representation labeled by that highest weight vector. Okay. All I need is to specify the highest weight vector. Okay. I keep applying the lowering operators.
In
and
general, is the highest weight vector unique in any linear algebra?
No. There are many highest weight vectors. Oh yeah. So for example, the highest weight for SU2, the highest weight vector for the spin half representation is something, okay, in which you can apply the lowering operator only once. Okay. The highest weight vector of the spin 1 representation is something you can apply the lowering operator twice, and so on. They are all different. Yeah. So I'll come to that thing. So there are many. So okay. So let me say that specifying a set of R integers, okay, specifies the representation, specifies a particular highest weight vector for me, and then I can construct the entire irreducible representation labeled by that highest weight vector or labeled by these R integers. So these are called that, yes.
So these R integers tells me that how many times I can lower the alpha I.
That's right. How many powers of E minus alpha I can apply to this given mu before I hit a 0. Yeah.
So that does not specify the depth of the let's say lowering operator.
Depth in the alpha direction it does. So if I start from mu and keep applying alpha 1, then I can only go up to Q1 number of steps. After that, I'll hit a 0. Okay. Similarly, I keep applying alpha 2, let's say, lowering operator E minus alpha 1. So E minus alpha 1 to the power or e minus alpha 2 to the power q2 up to that much will not annihilate the this guy mu, okay, but e minus alpha 2 to the power q2 plus 1 will annihilate this one. So this uniquely specifies, in fact, the highest weight.
So
Yes.
to get the entire algebra, we need the representation of all the highest weight vectors.
No. So this is specifying this already gives me one representation. I'll give you some examples, okay, and so I'll explain this one a little better. In case of SU3, r is equal to 2, okay. So this 1 comma 0, okay, that corresponds to the defining representation, which is also called 3, okay. 0 comma 1 is something that is called the complex representation. That's another 3-dimensional representation which is obtained by taking complex conjugation, okay. Then 1 comma 1, okay, this is some octet and so on.
And is it always
Yes.
is it always possible to find a fundamental representation?
Yes. Well, so let me say this again. So first of all, if there is a highest weight vector mu, that will have some unique non-zero integers, okay, which tells you about the depths of the various towers, okay. The other way around is also true, that if you are given r positive integers, you can construct a mu out of these, okay. That is to say, there is a solution of this equation for any r positive integers, okay, so that this is the highest weight. I mean, so there is a solution of this. So it is both ways. Given a mu, you can find out the q's, a set of q's. Given a q, you can find a mu. Yes.
You know, for a particular algebra, there are several possible highest weight vectors.
Oh yeah, many.
Yeah.
I mean, infinite
But
number.
What we have here is that for one highest weight vectors, there are several possible ways of going down in alpha, and the number of ways we can go down. So this will give us all the vectors which are linked to that highest weight vector. Like this could be something else altogether. Right?
Let me go to this. So in case of SU3, there are all these irreducible representations in which m and n are arbitrary integers, and I'll also construct this mn algebra today by taking tensor products of these things. So this mn can be obtained by taking 1 comma 0 m times and 0 comma 1 n times, okay, and I'll see how that goes, okay. This more or less follows by Leibniz rule, okay, because you know it's like, I'll come to that, okay. So this is how, so I'll come to this, okay. This can be explicitly constructed once the fundamental representations are, so the fundamental representations exist, okay, again by this uniqueness theorem, that any set of integers, okay, provides yes.
For a given representation, is the R fixed?
For a given the R is some property of the Lie algebra. So of course the representation does not care, but you may say what is the dimension of the representation. That of course depends on what.
The length of the vector is always same. Fixed.
That's right. The dimensionality of these vectors is always r-dimensional. So we are always, you know, sort of moving around in some r-dimensional vector space. In fact, the points. Maybe there's something that one can already say is that So if you so if alphas are supposed to span some lattice, integer lattice called the root lattice. Then this defines vectors in something called the dual lattice. Okay. So if you for the moment forget about this complication coming from the various lengths, let's say this is equal to 1, then, or let's say these guys, you take some convention, okay, it's not true actually, but suppose for the moment that all of these guys were 2, okay, then you have some basis vectors alpha I, okay, whose integer linear combinations will give you something called the root lattice. Now you might ask that is there another lattice whose points, any point of whose, which lattice, when dotted with these the basis vectors of the original lattice gives you integers. Okay. That thing is called a dual lattice. Okay. So this, yeah. So this you have probably encountered in solid state. Okay. So anyway, good. So so the point that I wanted to make is that these play an important role, these things, fundamental representations, and in case of SU3, okay, so I have already told you what this one, well, I have not explained this, but I will do that in just a moment, and I'll explain also this, what this notation is 3 star, etc. And at the moment, I just wanted to say that there exist special representations like this with Dynkin labels with 1 and 0 everywhere else, 0 and only 1 here. And I want to say something further, which is the following, that without proof at the moment, is that let us say this I call D1, that this representation I call D1, this I call D2, D2, this I called DR. And then the and the corresponding weights I will call these things as mu 1, mu 2, mu r. Okay. So these are the Dynkin labels and these are the corresponding special weights. Okay. Remember that corresponding to any set of integers there is a highest weight. So if I take these guys with only the first entry as 1, okay, the Dynkin label like that, let me call that particular special highest weight as mu 1, okay, and everybody else like that. Then because this is a linear relation, you can prove this very easily, that mu is equal to qi mu I equal to 1 to r. Okay, that is easy to show. Okay, this just follows from the linearity of this thing. If you add in the space of mu's, then that is equivalent to adding in the space of q's. Okay, so this fact tells you that this highest weight mu can be obtained by taking d1 times and d2 q2 times, etc. Okay, by taking a tensor product of these things. Why? Because let us say that I apply any one of the Cartan subalgebra elements on this object. Okay, so these are some states which are like the highest weight vector of each one of these highest weight. So one way of ensuring that so D1 has a highest weight vector which is this mu1, right? So let me call this just mu1. let me take the highest weight vector of everybody, then you can be sure that what you have got is a highest weight vector. This is what we did in our Klebs-Gordon game, that when you have the plus and plus, okay, that was definitely a highest weight vector because each one of them was. So if we apply the raising operator, okay, it will apply by Leibniz rule, and therefore it will be 0. So what you do here is similarly the plus was a highest weight vector of SU2. Okay, now this guy is a highest weight vector of whatever the generally algebra that you have. So it's like that, and then mu1 blah blah blah, mu1 q1 number of times, then mu2 q2 number of times, etc., etc. Okay. Now we apply your any of the raising operators, E alpha, which is the positive, alpha is taken to be a positive root. Then this of course will annihilate it. So this will be a highest weight vector. Okay. So first of all, that much is clear that this is a highest weight vector. Now we want to know the following thing, that is this relation true? Okay. So to see that, you apply the Karta subalgebra elements. Then in particular, let us say you apply H1 on this. Okay. What will that do? That will apply by Leibniz rule again. So it will pick up exactly mu1 from here, mu1 of 1. Okay. And this is mu1 of 2, so hi. So it will pick up mu1 of I so many times, q1 times, and then it will pick up from here q2 times mu2 of I, etc., etc. And then you rewrite these things in vector notations, you got this. Okay. So therefore, we proved this very important result, that, okay, by the way, these are called Dynkin labels. I don't know whether I said this. These are called Dynkin labels of an irrep. This is a very important concept, that this is a unique representation, this Dynkin labels, which is a set of integers, ordered set of integers. This is a unique characterization of irreducible representations. Okay. And I also told you how these representations like q1, q2, qr can be obtained. Okay, it can be obtained by tensor product of such things. Okay, namely, yes.
Why would it be an irrepresentation when we are taking tensor product of many irreps? It need not be an irrep.
Need not be a?
Irrep. Why should it be an irrep?
It would be an irrep because, good point, because we are starting from like this. If you started anywhere else, so remember what we do is to keep applying the lowering operators. Whatever we get, we take only that. Okay. Anything else that might appear they will appear lower on. So we are starting on the top. Okay. Whatever we get, that's a very important question. Yes.
Because you are applying the Cartan subalgebra generator HI, that will always generate a simple weight.
No, this only says that this has a weight. This only says that this is an eigenvector of the HI. But it does not tell you that, see, his question is the following, that I take this tensor product decomposition. We found that the spin half cross spin half thing, okay, that has 1 as well as 0. Okay. Why am I singling out only 1? The answer to that is that if I start at the highest weight representation and apply J minus, whatever I get, that's an irrep. It has to be an irrep because all of these are connected by J minuses or J pluses. Okay, that's the answer. Because so I have to make sure that I start from the highest weight vectors. But as you know, so it's not, so you know, so maybe one has to say it carefully. One has to say it carefully that this representation space has many other things, okay? But the irrep which is constructed out of the highest weight vector is an irrep. So that's a good point. Okay, good. So we gave a mechanism now of how to construct irreducible representations. So let me just tell you how to get a feel for the fundamental representations. In particular, we will explain now our old friend, this 103. So the defining representation. So maybe I should say this: the defining representation of SU3. The defining representation of SU3 will turn out to be 1, 0 in this Dynkin level. Let's see how that works.
A somewhat peripheral question.
Yes.
What does the underline in general mean when you, let's say the underline over a 3?
Mm-hmm.
For a
Oh, this underline, yeah, forget about this. This is supposed to be a poor man's boldface. You are supposed to do boldface 3, but you can't write boldface on the blackboard, so you just underline it. So
What is different between 3 and 3 star?
I'll tell you. So that's important. So it appears only from SU3 onwards. SU2 does not have it. Okay. In SU2, the 2 star is in fact identical to 2. Okay.
You have 3 Cartan or the 3 diagonal operators in the Cartan subtable. Then you can write it as, or the rank is 3 basically. So
yeah. So you can have So you can have 1, 0, 0, 0, 1, 0, and 0, 0, 1. Yeah.
then you cannot specify 3 star or 4 star or something.
No. So you can then, even then, you can have 1, 0, 0 being the complex conjugate of 0, 0, 1.
And what about the 0, 1, 0?
Yeah, let me try to remember. Yeah, it is probably a real representation. I think it's probably not a complex representation, but I'm saying it. I'll verify it next time. I think it's a real representation, but can't be completely sure.
Whether you call the 0, 0, 1 to be real and then 1, 0, 0 will be your complex. I mean, this is just a convention.
No. It's much more than a convention. It's actually a construction. So I'll come to that in a moment. It depends on how the weight vectors change from this one to this one. Okay, so they get reflected, about the origin. Okay, so this is what we'll do in the rest of the thing. I think that's all I can probably do today. So let's do this carefully. Okay. We are going to identify this 1, 0 as the defining representation. The defining representation, the weights of the defining representation, we wrote down as an equilateral triangle, okay, several lectures ago. Okay, so those are the following. So the defining representation, remember, it was like this. So it was like this, and this. Okay, this guy was half 2 root 3, and this fellow was minus half 1 over 2 root 3, and this fellow was 0 minus minus 1 by root 3. if I wrote it correctly. This is what we got. Okay. Now, let us say that you are sweeping these roots, these weights. So, these are weights. So, what are weights? Weights are weights label simultaneous eigenvectors of H1 and H2, okay, and these are the eigenvalues. Okay. Now, suppose that I am sweeping these weights starting from the right. Okay. So, this clearly is the highest weight vector. Okay. Why? Because any raising operator, you know, the roots are directed, the positive roots are all directed towards the right. Okay. So, this one, for instance, may not be at a highest weight vector, because when I apply a root vector to it, okay. So let me draw the, let me just draw the how the root system was. So the root system was like this. This was a regular hexagon. Look it up. Yeah, so these were the simple roots. These two were the simple roots. This was the one positive root, and they are minuses, right? So this is how the root system was of SU3, and this, right? This. So this and this were the simple roots. So you can see more or less by construction, that's how we constructed the roots. Remember that we took differences between these things. Okay. So clearly, if you apply this, okay, this right moving horizontal vector, you will apply, you will reach here, because the lengths of these things, okay, we constructed like that. Okay, and so what I am trying to say is the following, that the rightmost weight has to be the highest weight vector. This much is clear, okay? Because all the positive roots, okay, have the x component positive. So when I take a vector like this and apply any positive root, okay, I must increase the x component of that weight. Okay, so I'll go more to the right. So the weight vector which cannot go any more to the right, which is the rightmost, has to be the highest weight vector. Okay, rightmost. Our definition of positivity was that it has to be on the right half plane, and if we are on the y-axis, then it has to be in the positive half of the upper half of the y-axis.
We have to check both, no? Along the alpha equation.
If it is along that thing, then we have to check that if there are several possibilities. That, but once we have got something, okay, that's already my highest weight vector. Okay, so this is the highest weight vector. Now, basically, I have to find out what is the so now I keep applying I keep applying the lowering operators on that. So there are two possible lowering operators corresponding to the two simple roots. I am only talking about those lowering operators. Okay, and what you will find is that the so this was one this was one, this is the one direction, this is what I called alpha 1, and this is something that I call alpha 2, okay. And
One will be along itself. So one.
yeah, I'm just wondering whether there's a convention thing. No, maybe this is what alpha 1 is. Yeah, maybe this is what alpha 1 is. So when I apply alpha 1 this way, of course it is 0, but when I apply alpha 1 this way, okay, which is the lowering operator, then I reach here. Okay, so I start from the highest weight vector. So I wrote in my notes something wrong. I think this is what my alpha 1 was, and this is what my alpha 2 was. Okay. So the point that I'm trying to make is that you can figure out from this diagram what the depth is. The depth is 1. Okay. After that it's 0. After that it's 0. So you take the highest weight vector, you find what the, and the alpha 2 is, sorry, what am I saying? This is alpha 1 and this is alpha 2. So alpha 1, so I'm applying the lowering operator corresponding to alpha 1, and I got something. That's correct. So this is alpha, so alpha 1 as a raising thing gives you 0, alpha 1 as a lowering, this gives you the other weight, and then of course it is 0, and alpha 2 as a raising operator gives you 0, of course, and alpha 2 as a lowering operator also gives you 0 because there's nothing there. Okay, and how do you generate this one? Of course, this one says that you can still apply the alpha 2 lowering operator on this, and you will get this. You will generate that. Okay, but there is no statement about that in the definition of the depth of the highest weight vector. So the depth of the highest weight vector in the alpha 1 direction is 1, in the alpha 2 direction is 0. Okay, so therefore this is the 1, 0 representation. Okay, it's clear? So of course you should actually not do this, you should do this algebraically. Okay, you just compute, you just keep using the master formula, mu dot alpha I divided by alpha I square, and that's your depth. Okay, you keep applying this, you will find that this is 0, this is 1, and 0. So therefore this representation, which corresponds to the defining representation, is 1, 0. Okay. So, and this is a 3-dimensional representation, so this is this 3. Okay, so 1, 0 is of course the unique label, 3 is just a dimension of the representation. And when you go to large enough dimensions, there are different Dynkin labels that could give rise to the same dimension. So dimension by itself, okay, may not uniquely tell you what the Dynkin labels are. Okay, it's the other way around. Given the Dynkin labels, you know the dimension. Oh Jesus. Okay, now how about the 0, 1? So 0, 1 turns out to be the complex conjugate of this representation. So for that I have to explain what a complex conjugate representation is. Okay, so so most generally, if you have in some representation, if you have TA, TB, these are the matrices with this structure constant, you can clearly show that if you, instead of these matrices, if you consider these matrices, they have the same commutation relation. Okay, let's do that. So let's check out whether this is true, whether this is true. So that's clear. Why? Because this is TA star, TB star, which is the same as TA, TB whole thing star. Okay, and that is nothing but I, F, A, B, C, TC star, and that's the same as that. Okay. So if there are representation matrices like that, then minus TA star also correspond to representation matrices like this. Okay, and so then very good. These are called complex conjugate representation, but let us now see that what this does.
This is true for real, but the structure constants are all real. And
Structure constants are all real. You can you know, make these statements also for the anti-Hermitian representations, in which structure constants are all real with an I here.
No, I mean,
Oh yeah, yeah.
structure
Oh,
constants,
indeed, indeed.
These are real.
Indeed. These guys are real numbers. That's given. Okay. Now, so what does this do to the Cartan subalgebra elements? Okay. So the Cartan subalgebra elements are already real. They are real matrices. Right. So think of SUN, for instance. So it's just you know, the yeah. So Cartan subalgebra elements for, so it was some 1 minus 1 0, and H2 was some 1 1 minus 2 with some 1 over square root of 3 or something like that. But these are real objects. Okay. So when you do this operation, the Cartan subalgebra elements just go to minuses of themselves. Therefore, the eigenvalues of this get flipped. Okay. So if this is the diagram for some representation, the flipped diagram would be the weights of the other representation. Okay. The other representation, the complex conjugate representation, namely that, so this was like this, and the other thing would be like this. Now, which one is the highest weight state? The rightmost. This guy is the highest weight state now of this representation. Okay. And now, which operator can I lower the, so is it alpha 1 or alpha 2 which lowers this? Alpha 2, I rubbed it off, but if you remember that this was the direction of alpha 2. Now alpha 2 reaches another weight, okay, and only 1. So the depth is 1. So this is 0, 1. So this is 0, 1. So therefore, we prove this, that 0 comma 1, which is the complex conjugate representation, is 3 star. Now, okay, so my time is basically up, but let me just make some basically remarks. And next time we'll talk about some the stuff that I said abstractly, how to get the higher Dynkin labels by tensor product decomposition. That we'll actually do, and that will basically finish the Klebs-Gordon for these things. And there is another important, so what we will do is to use explicit tensor notations. And by the way, I forgot to say that these are all simple generalizations of what we do for SU2. Okay, in case of SU2, okay, there is a fundamental representation which is a spin half representation. Why is that this fundamental representation? Because if I take the highest weight vector, namely half comma half, and apply j minus 1s, then I get this, but application of this further gives 0. So the length of this is 1. Okay. So this is 1 comma 0. So this the Dynkin label of the spin half representation is 1 comma 0. Okay. So let me ask you, what is the more normal way of understanding 3 comma 0? Spin 3 half. It is spin 3 half because I start from 3 by 2, then I go to half, then I go to minus half, then I go to minus 3 by 2, and then finished. Okay, then I get annihilated here, and here, of course, if I go this way. So fundamental representations, what they are doing, are they are essentially chasing, okay, a particular SU2 chain. Okay. Yes.
It's just 1 and 3. It's not 1 comma 0. It's rank 1. SU2 is rank 1.
Yes. Oh, sorry. Excuse me. Thanks a lot. Thank you. The Dynkin label has only one thing. So it's 1. Thanks a lot. So Dynkin label has only 1 or 3, etc., etc. So that gives you the depth of the tower. Okay. Starting from the highest weight vector. So these are the, so what the fundamental representations are essentially like the spin half representations for each of these SU2s. Okay, that's the important point that I should make. Okay, and the reason why you are able to take a tensor product of all these fundamental representations to build more complicated representations is the same way as it happened for SU2. If you take spin half, you can obtain any representation, okay, by taking tensor product of spin halves, anything. Okay. So, and if you take, but you have to ensure that you have plus whatever, and you start from there. Okay, and for SU2 there is only 1, so you just go straight, zoom through, whatever you get is a one-dimensional linear array of weight vectors. In case of the SU2, for example, that you can go this way or you can go that way, the stuff that we were doing. So there are 2 different SU2 chains, okay, labeled by the 2 simple roots, okay, and that's the fundamental representation. Okay, next time we will talk about tensor product representation, and another important representation of irreps, which is called Young tableau. Okay, and that gives you also a different way of understanding tensor product representations. So that will basically more or less wrap up, and after that I will hopefully mention or work out some applications. Okay.